Hello, this is my theory of grand unified physics. I'll just state my results, I'll proceed to derive principles from them. The universe is essentially 36 statements, taken 6 by 6 and 4 by 9, and 27 of them fit into a category, and 9 are continuity equations. And the 4 categories they fit into in 9s are, which fits into 6 categories, being physics, math, logic, biology, psychology, and theology, with the seventh being computer science. I think is the seventh one. Actually, theology, more properly, the seventh. But with those proper states of mind, you can see that um, the statements are strange to the human observer, maybe because they say things like nothing can exist, nothing is impossible, nothing is possible, contradictions don't exist, nothing is real, and like different things like that. It's basically my contention that the universe is divided into disciplines, and that physics is fundamentally imaginary, math is fundamentally nothing, and philosophy is fundamentally negative, meaning that it tries to minimalize itself, be nothing at all, and be purely imaginary or fictitious in nature, obeying the laws of complex numbers. That's basically how I evolved my theory. The theory should be considered a little bit strange because you wonder how I got it, how I knew that there were 36 variables or statements. 6 is a perfect number, and 6 squared, there's something special about squares and cubes that make those numbers aesthetic. For instance, cubes allow juxtaposition while retaining one thing as constant. That's why there's 3 forces, 3 dimensions, 3 space dimensions, uh, the weak, the electro weak, the strong, and the gravitational force, and things of that order, is basically because it's the nature of threes. The nature of two is a binding clause. It forces something into a measured observable, and that's the reason twos play a role. In general, I've found that the first 6 numbers play a role in the measurable observables of physics. And the seventh number 7, is extraneous, being outside the domain of reality. Reality is a comprehensive word because it includes math, physics, philosophy, logic, and things of that order. So taking that into account, you form a more congruent picture of the universe. But that statements, you can kind of see how it evolves when you say nothing is impossible, nothing is possible. You can derive the Heisenberg uncertainty principle from that. Just from a statement that it contradicts itself seemingly, but each one of the statements essentially says two things. Because when you say that nothing is impossible, you're saying that no thing, like no such thing as a state of nothing as emptiness, is not possible. You're also saying that no particular item is possible. So there's two ways of dividing the definition of that statement, two ways of interpreting it. And that essentially is the crux of my theory, is that everything has two definitions or interpretations. In fact, it's been a surprise to physicists that there are two ways of formulating quantum field theory. It's my general supposition that everything in physics needs to be shown in two different ways, and that nothing is true if it can only be shown in one way, in one completely different way. You need two completely different ways of deriving everything, else it isn't true. At first, you might say that this was causal, this involved a proverse and a converse. That's not really what it is, but you can think of it that way because it helps enhance the picture, making the universe seem inevitable. And that's something we should look for in a coherent theory of the universe, that it explains why things exist when you can easily say that nothing should exist, that also that it explains why you still have nothing at any rate anyways. Like the force in the universe is always zero because it cancels. Likewise, the energy and the momentum probably cancel too, or very nearly. So you can say things like that, and it's important to be able to say that so that physics doesn't seem impossible. because just saying that matter should exist is a little bit strange. But also, you should ask the coherent theory of the universe. You should ask yourself what you want from it, whether it should be logical, consistent, simple. I would definitely say that 36 equations is not particularly simple. If you saw the number of experiments they're conducting at Caltech and MIT and places like that, you'd say that's probably a breakthrough of its own magnitude. Because with the spread of observed particles and particle creation energies, you'd think there would be 1,000 equations or something, and there's not. A lot of physicists used to dream that it might just be a bifurcation process or a logical process of ones and zeros merging and splitting. There might even be a chain of rings connected to each other and breaking. It's essentially how quantum superstrings work. They're just rings or lines, threads or lines, rings. And that's the way you develop the difference between a fermion and a boson. My theory doesn't really get into what a fermion and a boson are. That theory is more quantum superstring theory. But it does offer a caveat if you really think about it. Quantum superstring theory predicts 26 dimensions. General relativity predicts 10 dimensions. Well, 26 plus 10 is 36. So you have your 36 equations or statements. So you can think of it that way. It's basically a little curiosity I noticed. Yeah, but other than that, it's basically my theory of physics. And the way I derived through it was very ponderous and tedious because when first I asked myself whether or not the universe should be mathematical, apparently it is partially mathematical. Math is a little bit strange because you can state it independent or at least mostly independent of physical objects. You could say that 2 plus 3 is always 5, regardless of what you're talking about. But even more generally, you can say that 2 plus 3 is 5, even without the scope of anything real, outside the scope of anything real. So you can say stuff like that. And so I had to be very careful in fastening my theory of the universe because I also had to account for the statement that nothing is real in the sense that since the universe began as a singularity, the Hawking-Penrose singularity theorem, and energies and the forces are always conserved, you can say that in a very real sense, the universe doesn't exist and never has. It's just kind of like an illusion built up of three things, that three things taken simultaneously together make reality, but in a very real sense, reality doesn't exist in individual components. It breaks down. Um, I also would like to say you have to think about things like the similarity in the number of forces and quarks and dimensions in Riemann space. That it's always in threes. That lends a considerable amount of credibility to the statement that the theory of the universe should be expressed in threes, or at least some function of three. At first, it seems very credible. It seems like an excellent idea. My theory indeed follows up on that. The universe is basically just a big 6 by 6 cube, or square rather. Actually, it's a square, but it's just a 6 by 6 square. And I have fashioned other ideas concerning the laws of physics, such as the three Riemann dimensions. Two of them are actually Mobius strips, and the third one is a double Mobius strip, meaning that you could collapse space onto itself so that it had no dimensions, only one side, even though it was a three-dimensional topological object, and yet you lost 2 dimensions. Within time and space being similar, time is just the quantum conjugate of space, meaning that under the Heisenberg uncertainty principle, you simply have one time dimension, one space dimension, and two Mobius strips. And even those, since the regular space dimension is two Mobius strips, as doubly inverted Mobius strip, you really have nothing at all. There's a bit of information loss when you think about why the universe distributes the energies equivalently without consideration for a topological orientation of the vectors. But other than that, it appears to make sense. I've always had a fondness for Mobius strips. It appears to be a very mature model. It's important to realize that nothing can exist. In physics, as a principle, every equation in physics should indicate that imaginary numbers are the fashion of physics, and nothing can exist without reference to the imaginary. And that this is a channel into taking a negative number and adding a positive number and getting nothing at all. It's just mathematical fashionism. But I'd say that's basically my theory. I come up with a lot of other 36 statements, like um, nothing is improbable, nothing is probable. Apparently, 12 of the equations are probabilistic, 12 of them are real statements, and 12 of them are fictitious statements. So you can divide them into 12s and 3s, 6s and 6s, and 9s and 4s categorically according to their structure, and wind up with a coherent, integrated model of reality. But once again, I would stress that it's important to understand these principles in terms of things like relativity and quantum mechanics and field theory and string theory. It's important to understand them in the context of something like that, where they're motivated from and where they're going, and whether or not you can derive the principles of physics from those equations or those statements all alone. I know you can derive quantum mechanics from it. It appears to be a little bit harder to derive electromagnetism or gravity from it, or the weak force or the strong force. Um, yeah, and at one point I had mused whether or not the universe might just be a three-dimensional fractal with the equivalent of a Mandelbrot set taken in 3 dimensions. It might actually be that. Kind of a strange take on it, considering how complex and how many parts it has. Then again, since a three-dimensional Mandelbrot set is impossible, because vectors have negative polarities in three-dimensional space when you add them together, because x, y, z can be added into nothing. And therefore, you get one written in terms of the other. You can't have polarity in a three-dimensional space. Maybe the thumb of rule of reality is that it has to allow for three-dimensional fractals, and that's all. I don't know. I couldn't say. I used to believe that most Newtonian potentials and EM potentials were actually just circles that actually had boundaries like Mandelbrot sets under the force of gravity. But it's important to ask yourself exactly what happens when gravity isn't, when things like motion and time are indeed zero or meaningless, when you're in absolutely free space. You have to deal with the fact that if anything did exist, it could be said to be moving infinitely fast or rotating infinitely fast, or if two things existed, they could be said to be rotating or arbitrarily far from each other. It appears the universe sprang into existence as a collision of two things or a splitting of one thing into three things. It doesn't appear to be possible that it began as two things. That's simply too strange. But I could be wrong. It might just be two things colliding. I consider that possibility. It seems reasonable. If they come from infinite distances, you can say they never knew each other. Therefore, if they, at some point, you could say they were arbitrarily close to each other, you get a repulsion term. It might be more stable than saying everything exploded into existence. But this is my theory. So that's basically what I have to say. I'm surprised this lecture isn't as long as my psychiatry theory. You'd think a theory of the universe would be a lot longer. Um, Considerable thought went into it, though. You start to begin to see electromagnetism and gravity as variations of each other, to the point where you might even say they're quantum fluctuations of each other. And there were a lot of things I read when I was a young man that influenced my belief in certain statements about the universe. It does appear to be bifurcating, but the way it does is strange because it appears to split into 9 terms instead of 2 or 3. So that being said, it appears to be a very unusual form of bifurcation. Um, yeah, but I used to read things like maybe the gravitational energy cancels the tension in free space or space under the influence of gravity. like the rest mass cancels the influence of the curvature of free space or matter influenced space, and that the universe may just be a quantum fluctuation. It has made a considerable impression on me. I consider my model more mature, but at the same time, you really could think of the universe as a quantum fluctuation. It's taken out of scale. And that's another delicate thing to be had. Is all the force laws are congruent with respect to scale. Meaning that if you make an electron twice as big, you make its diameter twice as big, you double the mass, the charge, and the strong force. Well, if that's congruent with space, basically what you've done is you said that it's scale free. So you have to watch out for that kind of thing. It appears that the universe is indeed scale free, but it's also time free, meaning that certain quantities are conserved. This is more a principle of Noether's theorem and canceling terms in Lagrangian. You have to ask yourself where these equations really came from, what the underlying symmetry is, and things like eigenvectors and eigenvalue and Hermitian matrices and adjoint matrices and complex conjugates and complex pairs. You have to ask yourself what the origin and structure of these equations is, because a mature theory would definitely take into account the category of reasoning used in deriving these equations, whether it's just a pure list of physical derivations or whether they're employing math at some stage. And a lot of scientists will tell you that quantum mechanics is essentially math. I would say it has a highly mathematical structure. Since it's inherently physics, it really is physics, but it does have a highly mathematical nature. So you could get away with saying it's math. It's not really math, but like if you get into mathematical physics, you'll probably be talking more about math than you will about physics. And people find quantum mechanics so confusing, they don't even like to think about what it may mean to say that something may be two things. In my theory, everything is two things, three things, four things, five things, and six things. I even ascribe different degrees to it. Of each thing, one reality, two measurements, no wait, two aspects, three measurements, four, five, and six. I forgot what I called them. I called five lives, and six anomalies or something. But it's basically just categorical count-offs to the perfect number six, and the perfect number three factorial, which is six, which is a very ideal number. And it's kind of funny to think the universe may be built up of the supposition that addition could be substituted for multiplication. You think about it, it's believable in a very high way because to the universe as a beginning state, multiplication and addition were indistinguishable, meaning the only things that could exist were things which obeyed that rule fundamentally. And it's even sharper to have a duplicate because then you could say it canceled. Kind of like saying if you see something twice, it's not as dangerous because you know it's there the first time. You respond better to it the second time. I spent a lot of time in high school and college studying duplicates. I didn't realize they had an application in physics, but apparently they do. A duplicate object is much less real than a single object. In other words, it's both redundant and it's also superfluous. Superfluous, meaning you don't need it and you don't have to need it. And that can be said about a lot of things, but in physics, it's very aesthetic to think about the universe as being very concise and minimalizing. Since it began from nothing, you might as well expect it to stay close to nothing. And indeed, it tries to do this. This is one of the hallmarks of my theory. The universe has always tried to minimalize itself. The fact that there's life in the universe is an expression of the fact that there's fractals, meaning that fractal is just basically something that repeats itself. But if you ask yourself what the stages are, the components are of a periodic wave function, for example, you can say it's a constant, a periodic term, and a constraint maybe, or something of that order, like an arm rotating around itself, like a fixed point or something. So there's ways to define it, break it down categorically. you'll find once again it's only in three things. Like there's a high point, a low point, and an intersection, and those things define a wave. So it's really that simple. And fourth dimension is just the wave returning to itself again. To the fourth dimension is redundant, and that's what we should see time as, is redundant. Indeed, you should ask yourself if time really is equivalent to space. It's differentiated by a constant in most physical theories, which is strange because Kaku's reduction of 11-dimensional matrices for the 11 constants in nature leaves one term undecided of the 12 terms, meaning that it's always algebraic. This might indeed be necessary just for the fact that the equations have to be variable so they can be minimalistic or allow for some variety. It's kind of a strange feature of that theory, what he did in his book Quantum Field Theory, because if you take the equations of physics and multiply them out in a certain way under a matrix law, you can reduce any one term into terms of any of the other 10 plus a variable. It might also mean that there's parts of physics we don't understand yet. I would generally say there's not that many layers to physics, as Feynman used to say. He said perhaps the universe is like an onion. There's many layers of reality or structure inherent within the universe. I would say between general relativity, the macro state like organic chemistry, the micro state like quantum mechanics, maybe subatomic physics, you can't have more than four state scales of reality. It's just a little bit too grandiose. There might be five if you think that five is a governing rule to the universe. It doesn't appear that life plays that much of a role in the universe's evolution. Certainly, life had to evolve because of fractals, and then be able to reason about it because, again, it's a fractal, and the universe has to make psychological sense of how it could exist in the first place. But other than that, you'd say life, the fact that we all have to die and stuff means that either God or someone wasn't really caring about it that much. So you have to wonder if life really does play that much of a role in reality. I'm not saying it does or it doesn't, but it's something you should think about from time to time, whether or not anyone out there really cares for us. And admittedly, I've taken fractals a good deal farther than most people have. I've also taken the idea that things should be taken in threes further than most people have. I've applied it to psychology profoundly, uh, and psychiatry. But I believe also threes is a critical number for physics as well. That being said, I should wrap up this lecture. It's my hope you get a chance to think about this and at least weigh the possibilities, come up with some of the 36 equations yourself. Remember, they have to be categorically divided into probably, I would say, even 18s. 1, 36, 18, 2, 3, 12, 4, 9, and 6, 6. I think that's 5 sets. I'm not certain. Probably only 4 sets. But let me see. 1, 2, 3, 4. Yeah, it's 5 sets. That being said, the universe might actually really have 5 scales of reality. I don't know. I can't imagine there being 2 scales of subatomic physics. There might be a physics we haven't discovered yet, like the physics of way outer space, where there's virtually nothing at all except a few free photons flying around. I used to think that if free space actually existed outside the universe, it would have to be infinitely dense, but it wouldn't matter because we'd be inside a Gaussian surface, and so the potential would either have to be linear or zero. I think it would be zero since nothing was contained in the Gaussian surface. So you could say abstruse things like that. That's why space-time is so flat without gravity, because there's an infinite mass, a shell of mass around us that constrains it to virtually absolute flatness. You might think it's ironic I don't consider problems like the cosmic microwave background and inflation and things like that. It was innovative for its time. I don't think Goeth's idea of the inflationary universe is really that revolutionary. It allowed for some new physical ideas, but it's really not the hallmark of what great physics is. Even the invention of superstrings wasn't that great, nor was quantum field theory. I'd say the only real breakthrough they made in the last 80 years is probably the Dirac delta function and exploitation of it. It's the first real insight they've shown into quantum mechanics, that at some point you have to reason that gravitational fluctuations within near empty space would lead to angular rotations that were infinitely sharp, meaning that if gravity were continuous at a very microscopic state, you'd get sharp peaks of very high density, however, scaled low but high enough in density at the micro scale to rotate things very sharply. And that's generally what I believe in, is that at some point quantum mechanics has to yield to gravity. And when the two are integrated, you get something very strange. It probably accounts for what the dark matter is, maybe a few other things. Yeah, there might actually be two more layers of subatomic physics we haven't discovered yet. But basically, when you start getting down to quarks and threes in the eightfold way, I think you're relatively close to a real theory of reality. These are very telling numbers about what reality is. There's only four Maxwell equations written as one, and three Newtonian equations and a continuity equation. You think of those as, I guess what I'm saying by that is that one of the Maxwell equations, or at least some topological integration of parts of them, must comprise the time dimension when mapped into Riemann space. Meaning the continuity equation is time and the three laws of Newton are x, y, z. That's the way I'm thinking nowadays. Like I said, it's a mystery to me how the Mobius strips that represent X and Y and the double Mobius strip that represents Z can be merged into something which is vector-wise indistinguishable from any other direction. I don't know whether it involves something which has no direction but has magnitude and yet acts like a vector anyway. It might be some very strange mathematical object we've never encountered before. And it may very well be that a fundamental theory of reality is forever beyond us, just because the quantum mechanics of having absolute uncertainty about what is knowable may lead to the fact that we may never know what reality is as a physical law. It might be written in physics that it's impossible to know reality because the scale is simply too small, and the fractal doesn't allow for an understanding of physical realities and completion. My guess is you could probably understand it if you really understood what you were doing. But I don't know, quarks may be comprised of other things. You think about the way physics has evolved when considering Dirac deltas, fuzzy Feynman diagrams, uh, continuous gravity, the Heisenberg uncertainty principle. Think about things like that. You're leading more into the statement that reality is unreal and that reality doesn't exist, and that what does exist is just a makeshift and richness and dimension, but scalars don't really exist. Things like that. And I don't necessarily find a problem thinking this way. You kind of think the universe always had to be nothing and always will be, or kind of like a wave vibrating, is what Penrose used to say. It's kind of like a string vibrating where the nodes were fixed in two black holes. In the first black hole, it exploded. The second universe expanded forever until you lost scales of angles and everything compressed again suddenly in kind of an ingenious fashion. The way I model the universe is different than Penrose. Penrose envisioned a nodal wave that kept on propagating like the universe would expand and contract over and over again. I see it as two universes separated by two black holes wound around itself in a Mobius strip in two dimensions, and a double Mobius strip in the third dimension, in which only one particle escapes, has an initial velocity, and then bifurcates into three different particles in nines as soon as it emerges from the other universe. See, that's the cleverness of the Penrose-Hawking theory. Although you could argue that the universe began as nothing, you could also say it had initial velocity because the continuity of something that vanished momentarily would also have continuity in the other universe that it came from, so that it would reappear eventually later. That's my insight into the Penrose theorems, and I think it's considerable, but I don't think it's going to get us over the heap entirely because we still have to account for what kind of symmetry existed within the early universe. Was it cylindrical, spherical, rectangular? I personally believe it has to be cylindrical. I'm highly leaning against spherical. I tend to believe the universe began as cylindrically symmetric, although I'm not sure how. But just little things like that concern me in my aesthetic theory of the universe, what it should be and ought to be. And that's a formal acknowledgement to quantum mechanics and quantum field theory, is that the more we study it, the less it seems to make sense. And so you could say, not that the universe doesn't make any sense, but that it's holistically unreal. Like it's just a kind of like three things, one thing which is actually three things. If you add together the three things in parts, it's nothing. But if you take it as a whole, all lumped simultaneously, then it's one thing again. So you're kind of like thinking in terms of splitting and that sort of thing. This is basically how I model the universe nowadays. I guess it's mature. I haven't really asked myself that. It's been a lot of fun deriving these equations. I think it's the most mature front ever put forward about the nature of the universe. And I think it's important to understand that the universe is part psychological, like part of a fractal. You can think of psychology as being a fractal effect. In other words, you might think of it as being more mathematical than physics, and that psychology is math and physics is logic or something like that order. I don't really think that's the case with either. Logic is a kind of strange science because in most forms of logic, something is either true or false. Well, if that's the case, it's only two-dimensional, so that's inherently unrealistic. I'm not saying there should be a third alternative in reality, but evidently the idea of nothing playing a role definitely appears to have some appeal in physics. But I'm just saying that you should wonder how far you're able to take something like logic and physics, like Aristotelian reasoning and the rule of fours and Aristotelian reasoning, things like that. And it's important to realize that physics is, it might actually be something that's incomplete, is what I begin to realize more and more. Something which is fundamentally incomplete without reference to something external. That's not to say that I believe in God. It just means that maybe there's something about the other universe we don't know, like um, all the energies are reversed, or all the negative states are their own antiparticles, or something weird like that, where the fundamental physics of the universe changes in the other universe. You could have something like that. For a long time, I considered alternatives, like what if something were quantized? We hadn't thought it was quantized before at the submicroscopic level, like angular momentum or space or time. For a long time, since about 2013, I was a proponent of the idea angular momentum was quantized. Recently, I begin to think it's more mass that's quantized than anything else. And those would produce a fascinating alternative to the continuity of general relativity. You'd probably force it to be vaguely quantum mechanical or at least very choppy, which probably, beyond a certain energy threshold, might make it more appealing for people to reason about. Because if you take the three body problem and reason that it's instantly chaotic, since most particles in the universe and systems are three or more particles, you're essentially dealing with three body problems. Well, those are instantly chaotic, and the more you get to the microscale, you find that at the fringe, they're even infinitely chaotic at the fringe, meaning that something that random would probably produce a pretty stark effect in quantum mechanics under the Heisenberg uncertainty principle, which is my belief. I'm not sure. You might also see something strange in electromagnetism or something. You might even be able to define electromagnetism or quantum mechanics in terms of something like that. I know you can get quantum mechanics from my theory of the universe. What it doesn't cover is EM, strong, weak, and gravitation. A lot of people would be tempted to say gravity is just an analog of electromagnetism, but the universe obeys the Einstein field equations, and even those aren't unique. There's an infinite set of Einstein field equations that might be plausible. So it's far from unique, and you think of that, you begin to realize that something which unique isn't unique is probably something which isn't plausible. Thinking that way, you might be able to reason that the whole of gravity is imaginary, but it has no real structure. You should just think of that as causative, that the universe is destroyed by nothing because it came from nothing. Additionally, I also think the universe began like an egg, thinking in terms of fractals again, since an egg is how a bird is born, the universe may have begun as an egg shaped symmetry, like a particle emerging from another particle, in the egg like shell symmetry. I wouldn't say that's the strongest evidence for that, but it's plausible if you really think about how prevalent fractals are. Well, that's basically all I have to say about physics this time. I've done a lot more work on it. It doesn't come to mind right now. Some of the work that I've done, I believe I've gone over most of it, or at least almost all of it. Surprised it only took this long. This is Ricky Smith logging out.